Assalamualaikum warahmatullahi wabarakatuh. For today, we would like to present about plastic optical fiber pitch sensor based on silica gel film. The research is conducted by Affa Rozana, Muhammad Falik and Y.My Sarah. We are from Applied Physics, Faculty of Science and Technology, USIM. Okay, so for an introduction, the optical fiber have a major role not only in communication but also in development of sensors. So here we have different types of sensor that can be done by using fiber optic, such as humidity sensor, alcohol sensor, UV sensor, and various type of sensor. So this is our fiber optic. We have core, and then cladding, and then we have jacket. So in order to become a fiber optic, we remove the jacket and play around with the cladding itself, whether you want to etch the cladding and coat with a material and so on. Okay, so here is our fiber optic, and then for the fiber optic itself, we have source, light source, whether LED or laser. And then we have power meter or detector. The detector itself is connected with electronic processing. Okay, so here is the light that propagate inside the fiber. We have core and cladding. So it depends on what type of fiber that you want to use for sensors. Okay, so this is the optical fiber classification. Alright, so here we have optical fiber sensor, and then for the type of fiber that we use is POF, which is plastic optical fiber, and then the type is multimode fiber. Alright, then for the geometry we use unclad and clad. Okay, for the unclad, which means that we remove the cladding. Alright, then beside that we also have tapered, side polish and bend. Okay, but for today presentation we use unclad. Then for the sensing location we use intrinsic. Okay, so which means that we play around with the geometry of the fiber, and then we must know the properties of the evanescent wave. Okay, for the coating we use a film that coat on our fiber optic. So the application, it depends on what type of application that you want to use for fiber optic. So for today we use a chemical and that in specific pH sensor. Okay, so this is a general view about fiber optic that based on sensor location. So here we have intrinsic. So the intrinsic itself is the modulation take place outside the fiber. So which means that the fiber itself is used to transport a light signal to and from the sensor head. Okay. For the intrinsic type, which means the internal property of the optical fiber itself converts the environmental changes into a modulation of light signal. Okay, so here we have several types. Okay, so for the first one is optoid, which means that we only use the fiber to propagate the light. We do not change the fiber itself. So we just use a reagent at the end of the fiber. Okay, and then we have B porous glass, which means that the fiber or the core itself, we change it by using a porous glass, porous core duct. Okay, with what type of with reagent, what type of material that you want to coat. Okay, and then active coat, which means the core itself we use for light to propagate, but we remove the cladding. Okay, so the cladding we coat with our reagent. And last is spectrometer evanescent, which means that we do not do a coating. We just use a light that propagate inside the fiber and react with another light. Okay, so here we do not coat the fiber itself. Methodology part and experimental setup. First, we prepare a silica gel by using sol gel technique, and then we determine the silicon component by using FTIR. Next, we prepare a sensing probe. We remove the jacket and then we etch our cladding and coat it with our silica gel at the end of our probe. Next, we determine the pH level of our analyte by using pH meter, and then we record or determine the refractive index of our analyte by using a refractometer. After that, we can do an experimental setup, which means that we connect our fiber probe with our light source and power meter by using a Y coupler. So the light that propagates inside the fiber will have a reaction at the end of our fiber and reflect back the light and received by our power meter. So the mechanism occurs at the end of our fiber. pH and refractive index measurement. Our analyte consists of Coca-Cola, tomato sauce, black coffee, tea, distilled water, soap, baking soda, and Clorox. The pH value is determined by using pH meter. The first graph is pH value versus analyte. The first one is Coca-Cola with pH of 3 have the highest concentration of hydrogen, while Clorox with pH 10 have the highest concentration of hydroxide. The second graph is refractive index versus pH value. We measured the refractive index by using refractometer. At pH 3, it have the highest refractive index because it have the highest concentration of hydrogen. So the value of refractive index is the highest. When the concentration of hydrogen is reduced, the refractive index also reduces until pH 7. At pH 8, 9, and 10, the concentration of hydroxide increase. So when the concentration increase, the value of the refractive index also increase. That's why we have the shape like this one. The higher the refractive index of the material, the slower will the light movement be through them. Here is fiber optic sensor where we use fiber probe as a sensor to test pH level of our analyte. So we have 5 testing. The gap between test 1 and test 2 is around 2 days, and the gap between test 2 and test 3 and test 3, 4 and 5 is around 5 minutes. So that's why you can see that the power output drop. Okay, so which means that we need longer recovery time. Okay, so here we have analytes that we have pH 3 and pH 10 that have very concentrated with hydrogen and hydroxide ion. Okay, so which means that they have high refractive index compared to pH 4, 5, and 6. Okay, so which means that when it have higher refractive index, the light that propagate inside the fiber tend to go outside of the core. Okay, so when the fiber itself the light itself tend to go outside of the fiber, so the power output here will reduce. Okay, so that's why the output power is reduced for pH 3 compared to 4, 5, and 6. Okay, so here is a graph, power output ratio versus refractive index. As you can see here, when we increase the refractive index here, the power output ratio increase. Okay, so which means that when the refractive index of our analyte increase, the light tend to go outside of the fiber. Okay, so that's why when the light tend to go outside of the fiber, the power output ratio will increase. Okay. Here is the sensitivity of our fiber probe. We do a comparison between uncoated and coated. Okay, so as you can see here, for the uncoated, the sensitivity is lower compared to coated. Okay, so the uncoated is around 0.0429 and the coated is 0.05. Here is evanescent coefficient. The evanescent field penetrates into both solution and evanescent wave absorbance occurs, in which it will increase as the concentration of the solution increase. As we know, pH at pH 3, the refractive index is higher compared to pH 4. So the evanescent coefficient is higher compared to 4, 5, and so on. When pH level is approaching 7, the output power increase and the evanescent coefficient decrease. The evanescent coefficient is high at 3 and 10 because they are concentrated with hydrogen and hydroxide ion. So here we know that the evanescent coefficient depend on the length of the fiber and the power output. So the power output depend on the refractive index of our analyte. Okay, penetration depth. So this is our fiber, and then penetration depth is from the core to the outside of the fiber. Okay, so this is the gap. In order to determine penetration depth, we must use this equation and insert the value of the wavelength, and then we have a refractive index of our core and refractive index of our surrounding. Okay, so according to Kejuania, the increase of the penetration depth can result in the increase of absorption of evanescent field by the absorbing medium. So it can lead to increase of the sensitivity of the sensor. So that is the importance of penetration depth. From the graph, as you can see here, when we increase the incident angle, the penetration depth will reduce. Right, around 700 nanometer, and reduce, it depends on the incident angle. Okay, so this is the incident angle that the light propagate inside the fiber. Conclusion is that any material which are capable of absorbing the particular wavelength of the incoming light inside the optical fiber will take the energy out of the evanescent wave. So first, it is better for the etching solution to dilute with the distilled water because we want to make a fiber probe, so we must make sure that the surface quality is good for sensing application. Okay, because it will affect the wave guiding process. And then the coated POF has a sensitivity of 0.0566, higher compared to uncoated POF, which has a sensitivity of 0.0429. Okay, so this is the reference that I use. Okay, thank you.